Okay, so this meeting is being recorded. We are talking about the series. Specifically, we are going to continue to discuss topic 11.3. We have discussed half of the content in 11.3, and we're going to continue to discuss this. But before I continue, I just want to remind you what we are talking about in case you have not been following very closely our topic. We are talking about series. Series is the summations of all the terms in a sequence from 1 to infinity. Sometimes it begins from 0, sometimes it begins from 1, it doesn't really matter. And we want to answer a simple question: is the series converge or it's not? So far we have discussed two types of series. The first series is geometric series. And for geometric series, it's very easy. For geometric series, the summation is in the form of AR power n minus 1. So this is a geometric series, and we know about geometric series very well. We know its convergence condition, that if R magnitude is less than 1, then the series would converge to A over 1 minus R. We also mentioned another series which is called the harmonic series. So we mentioned harmonic series, and then we use a theorem that says a series that is formed from terms that is non-negative, then the series would be convergent if it's bounded from above. If the sequence of a series is bounded from above, then the series would converge. And then we show that the harmonic series, which is in the form of 1 over n, diverges, because we can prove that the harmonic series is not bounded from above. Therefore, the harmonic series is divergent. So far, these are the important message that we have seen and we have discussed. Okay, so this was what we have discussed yesterday. So what is going to discuss next for the rest of today's lecture and probably tomorrow's lecture is to answer a very simple question. I give you a series and you tell me whether the series converges or not. And we are going to learn I think 1, 2, 3, 4, 5, probably 5 different types of tools that will allow us to answer the questions of whether a given series is convergent or not. So today's topic is about the first tricks to check the convergence of a series, which is more general. So what I'm saying more general is that this geometric series is not as general. Not all series are in the form of a geometric series. So for example, if I give you a series like this, say a series like this, can you tell me whether this series is convergent or it is divergent? So more specifically, more generally, we will be doing something like more complicated, like this one. I give you this series, you tell me whether it is convergent or it is not. So the tricks here we are going to learn to test the convergence of a series is what we call an integral test. Integral test is again the first tools that we are going to learn to check whether a series is convergent. So, but this integral test is specific. It's only applied to a series. See, the series is like this. It is applied to a series where all the terms are positive. And for this integral test, it applies to not only the series, the condition to apply the integral test is that the series has to be contain only positive terms. Okay, it cannot contain negative terms. And then the other conditions to apply an integral test is that the terms on the series, like, so you can imagine that a series is formed from an sequence. So this kind of sequence, if you plot it onto an x and y axis, so the sequence has to be such that when n grows, the sequence should generally become smaller and smaller in magnitude. Okay, so this is a very specific type of sequence. So if you have this kind of sequence, Well, to be more specific, the sequence in the series, the sequence that form the series, have to be such that whenever n is larger than a certain number of n, then the terms an in the series should become smaller and smaller. Right? Not all sequences are like that, but if you have such a sequence, then it will be quite easy to check for the integral for the convergence of the sequence. So what the theorem says is that if you have a sequence that is like what I described there, you can use the theorem 9, the integral test. So you have an sequence an which is all positive, and suppose if you find out that for certain number of n, as long as the small n, that is the index on the n, is larger or equal than n, you can map the functions of fx into an such that the values of f at f of x equals to n coincide with the values of the term an, and then the function of fx is decreasing for x larger or equal to n. Then you can easily find out whether the series S, which is the sum of an, converges or not by performing the integrations on the functions from n to infinity. Okay, so this is basically what this theorem says. So if you don't understand me, it doesn't matter. I think theoretically, operationally speaking, it's very easy. So what you do is that if you have a sequence an that you know that is all positive in terms, all its terms are positive, and then the an can be mapped to a function. Then we are going to integrate the function. Now here, what we want is to find out if the series converges or not. In order to check the convergence of the series, you don't look at the series directly, but you try to find another function, fx. This fx has to be invented. So you have to invent a function so that the functions f that you invent coincide with the values of the term an whenever x is equal to n, right? So that is actually not that difficult. Given any an expressions, you can always find fx. For example, if the term in the series is such that it say, for example, 1 over n squared. And in this case, it is quite sure that all terms are positive. And then as long as the n is equals or larger than n, then you can form a function fx such that it is equal to 1 over x squared, right? So given this sequence, you can try to form a function fx which is in the same form as 1 over n squared, but instead of n, the arguments or the variables, the independent variables, is x. Right? So here f plays the role of an, and x plays the role of the index. So what you do here is that given this one, you write down an corresponding function. Then you look at the functions, and then you try to integrate the function for x equals to 1 and go all the way up to infinity. So that will allows you to integrate these functions from 1 to infinity. And then you will try to see what is the integration. So there are only two possibilities. Either the integrations at infinity for the function f converge or diverge. Right? You can either converge or diverge. There's no other way around. Then if this integrations converges, that means the sum, that means the series that is formed from the sequence term n converges. If the integrations of the functions from n to infinity, the n here meaning n, capital N equals to 1. If this is divergent, then so is the sum is divergent. So that is basically what the theorem 9 says. It's very easy, right? So for example, you have what we call an P series. Now the P series is one of the very important case of series. Case here means the result of the P series would be used again and again. We are going to use these results of a P series later on. So when we continue to discuss the topics, you'll be seeing that we have to recycle many previously known results that we have already discussed. For example, the harmonic series is divergent. So such a result will be repeatedly used in when we consider other cases. And then the P series also, the result of P series would also be used to allows us to obtain the calculations of other series. Now the P series is like this. The P series is a sum of the term 1 over n, in which the n is raised to a constant p. Here p is a number, it's a fixed number. The variable here is n, so n runs from 1 to infinity. But p is a number, so p could either be 1, larger than 1, or less than 1. Okay, so there are only 3 possibilities for p. So this is called a P series. When I ask you what is a P series, you don't say I don't know. The P series is very simple. It's just a series where the term in the series an is given by 1 over n raised to n constant of p. Okay, so you ask the question, is the P series convergent? The answer is it depends very much on the values of p. If p is an positive number larger than 1, then the P series will converge. If P is equals or less than 1, then the series will diverge. And you can prove this quite easily using the theorem number 9. So what you do is that you perform an integration on the P series. So this is what we are going to do. Say you have this S, which is the P series, 1 over n raised to the power of p. So the summation actually is assuming n going from 1 to infinity. Okay, so to apply the theorem number 9, we look at the P series, and it's quite sure that the P series fulfill the conditions that the term in the P series, which is the an, which is 1 over np, is always positive and it is decreasing. Therefore, we can apply the integral test to this. So to this end, you invent a function fx that coincides with the term an, such that when x is equals to n, that is when x is an integer, well, what it means is if x takes on the values of integer, then the function of f should coincide with the values of the Pn. So you can imagine that this would be like you have say for example p equals to 1, then the P series will be like this, right? So because it would be like 1 over n, right? So if this is 1, then this is 2, this is 3, this is 4, this is 5, then this would be 1, this would be 1/2, then this would be 1/3. So basically this is an harmonic series. Then you invent a function fx which is equals to 1 over x power p. So this function is a function that begins from n equals to 1, and then it will be a continuous function. So there are two functions, there are two things here. First is the continuous function fx, which is equal to 1 over x power p. Then you have the discrete values of an that is represented by the point. So you invent a function, a continuous function that goes through all the point of an. Then now you look at the functions and you try to integrate the functions. So here the function that is chosen is 1 over x power p. Therefore, to determine the convergence of the P series, you start off with n equals to 1, right? So here, when the capital N is larger and or equals to 1, then the function f coincides with the P series, and you take all the way to infinity. So what is f of x? F of x is x power p, where p is a constant. Then you integrate it from 1 to infinity. But here you don't take it to infinity, you say first I integrate from 1 to b, where b is a limit, is a number. After that, then only I take b to infinity. So that is how you integrate the functions of fx from 1 to infinity. So integrate from 1 to b first, only then in the second step you take b to infinity. That is how you evaluate the integration from 1 to infinity. So the integration of x power minus p, the integration of it is actually very simple. So we have to divide the integrations into 3 conditions. The first condition is we assume p is larger than 1. Then only we consider the integration of p less than 1. And lastly, we'll consider the condition where p is equal to 1. So let us assume that p is larger than 1. So if p is larger than 1, then this integration becomes this, p to infinity. So here you have x raised to the power of 1 plus p, 1 minus p. Okay, that is what you get. And then you have 1 over p. Right? So this is the integrations, and you evaluate x at 1 and evaluate at b. So that is the result of the integration. Integrating x power minus p give you x power minus p plus 1, which is written as 1 minus p divided by minus p plus 1. So this is the result. Now here you have to be very careful, right? So here p is a constant and the variable is b. So you have to replace b into the x. But you have to look at this one, and since p is assumed to be larger than 1, so 1 minus p is actually a negative number. Okay, yeah, am I right? So then we try to rearrange it a little bit so that it looks like 1 over infinity. Then, sorry, I think I would write this as 1 over p, which is a constant, which has nothing to do with b. Then you take the limit, b goes to infinity. Then x raised to the power 1 minus p could be then written as x p minus 1. Right? So it looks much more comfortable in that way because p minus 1 is a positive number because p is larger than 1. So p minus 1 is positive. Right? So not a positive, it's a positive because p is assumed to be larger than 1. And then you take the limit of x between 1 to b. Okay, so you write this further a little bit, then it becomes what? It becomes limit of b goes to infinity. Then this is evaluations of x, which is we replace. So now you replace x by b raised to the power of p minus 1, and then minus 1. I think this is like this. Okay, so here the 1 that appears here is coming from here, right? So what it means here is that you replace 1 into here. So 1 raised to a power of p minus 1 is 1, right? So 1 raised to any power will always be equal to 1. Okay, so now we are almost there. Then what can you say about this? This is 1 over p, and then you have a limit of b going to infinity, and you have 1 over b raised to some power p minus 1 minus 1. Okay, so what can you say about that? The answer is this. You just have to let me know whether this limit is convergent or it is not. Now, here you have to be careful. Okay, p minus 1 is a number, which is a positive number. It could be something, maybe 0.1, 0.5, 0. Whatever, or it could be like 25. But it must be a positive number. So you have a 1 over b, which is going to, where the b is going to drag to infinity. So since the b is sitting in the denominator, whatever power it raised to, it will not affect the behaviors that this term is going to be 0 when b shoots to infinity, right? So you have the denominator that is going to become extremely large. Therefore, the condition here is that this is going to be 0. So what you have is it will become a number, which is maybe 1 minus p. Okay, so which is p minus 1. So that means p, which is a number larger than 1, shows that the integrations of the function x power minus p for p larger than 1, it converges to a number. So what number of it is not important, but it must converge to something. So according to the theorem number 4 here, so the theorem number 9 here, then if the integrations of the functions from n to infinity converges, so is the series converge. Therefore, we come to the conclusions that the p series converges for p larger than 1. So now you can continue to do the same argument, but you consider, for example, p is less than 1. So if you do p less than 1, then what you get from this integration would be slightly different. So it will become, say, for a case of p less than 1, the integrations of the functions fx from 1 to infinity could be carried out. I think it is similar to the calculation I just shown, but it will be equals to, I think it will be minus 1 over 1 minus p, and the limit would be, I think it will be, the limit would be given as, what is that? B raised to, I think that is 1 here. Then you have b raised to n power of p minus 1. Okay, so I think that is what happened when p is less than 1. Then here it become limit of p minus 1 is less than 1. That means it's negative, right? So it means this will become negative. So it becomes b raised to the power of 1 minus p with 1. So I think this is what you would get when p is a negative number. So basically, you just look at the sign of p minus 1. If p is less than 1, then this is a negative. So 1 over b raised to some negative number is just b raised to the power of 1 minus p. Just revert the sign so that I can rewrite 1 over b raised to the power minus 1 over b raised to the power p minus 1 become b raised to the power 1 minus p. So that here 1 minus p is a positive number, and you are going to make b going to infinity, right? So the b is going to infinity. So what do you get? You get that this term, if b is a number that's going to be infinity, and 1 minus p is a number. So you are raising b to some finite power, which is positive. 1 minus p is a positive number, remember. 1 minus p is positive. So you have a situations where b raised to the power of some number, and you are going to make b go infinity. Therefore, what happened to this term is that it's going to blow up when b goes to infinity. Okay, so therefore, this term is obviously it is going to blow up and it's going to be infinity. So whatever number it is not important, but we know that it's going to blow up to infinity when b is taken to infinity. Therefore, the conclusion is for the case where where p is negative, the p series according to this integral test is infinity. So we have just proven that the p series would converge if p is less than 1, and if p is larger than 1, then the p series is going to blow up. How about the case where p equals to 1? So according to the p series definition, this is equals to 1 n power p, right? So if p is equals to 1, this is nothing but just the harmonic series. And we have already proven harmonic series is divergent using the previous theorem that we discussed yesterday. So for p equals to 1, then you have harmonic series, and harmonic series is divergent. Therefore, we have finished discuss example 3 to prove the p series to be convergent when p is larger than 1, and it's divergent when p is equals or less than 1. So you have to remember the p series result. because we're going to recycle it again. You will encounter P series again and again when we check for the convergence of other series. Okay, so this is another example. It's very simple. You have these questions of an series, an, where an is a number which is 1 over n squared plus 1. And you ask this question, is the series of the summation of term an, where an is 1 over n squared plus 1, converge or not? So you have to look at this and then come up with your own test. So up to now, we only learned one test, which is the integral test. Of course, you will use the integral test to obtain the convergence or divergence of this series. Therefore, the first thing you do is map this term an to a function. When I say map, that means you have invent a continuous function with a variable x, such that when x is equal to n, the function coincides with an. So obviously, the form of the function they have to choose would be just like this. Right. So here you can see quite well that as long as n is larger or equal to 1, then f of n is equal to an. So now we have chosen a right function. Then what you do is just integrate the functions from 1 to infinity and see what you get. So this is the integration. We have seen it again and again. So you integrate this for the x from 1 to infinity, then you carry out the integrations. So you have know how to carry out this integration. We have seen this for many, many times already. I think this is integrations that involve, I think, arctangent or something like that. So yeah, I think it's equal to arctangent. So the integration of this is the integration of arctangent. And when you set the b to infinity corresponds to this limit, then you find that the integrations of fx goes to a positive number. Okay, so I'm not going to show you the detail, but the integration of 1 over x squared for x from 1 to b is arctangent of x. And you evaluate at b and 1, then you take b to infinity. So finally, you show that this integration is convergent to pi over 4. Therefore, you say this series converges. Now, it's a very, very important idea that you have to understand. The integral test only tests for the convergence. It does not really tell you the values of convergence of a sequence, okay, of a series, sorry. So it doesn't mean that the integral test converge to pi over 4. It doesn't mean that this series also converge to a number of pi over 4. It is not. It is something else. The integral test only answer part of the questions. It only answer the question of whether the series is convergent or is not. Okay. The next question, which is the numerical values of the convergence, is not to be calculated using the convergence test. Convergence test is a test. It does not tell you the values of the convergence. But if you want to know the values of the convergence, what do? You use Mathematica. I think Mathematica allows you to calculate the convergence of this series. I'm not sure whether this could be done, but let's just try it out. The Mathematica not only tells you whether the series converges, it also should tells you what the values of the convergence is. Let's try and see if I can calculate the convergence of this series 1 over whatever. Okay. Okay, so the Mathematica to calculate the limit of this series is not trivial, right? So first of all, you have to calculate the partial sum for the sequence for the series of 1 over k squared plus 1. And then you set the sum to run from 1 to n so that these highlighted portions will calculate the sum of the partial, will calculate the partial sum of the sequence 1 over k squared plus 1 from 1 to n, so that this highlighted portion is a function of n. Then only you ask Mathematica to calculate this function of n by setting n to infinity. So you find out that the number that this sequence converges to is different than the one that is obtained from the integral test. So here I think the answer for the integral test for this is pi over 4, but the actual value where it converges to is not pi over 4. Okay, so that is the sections on the integral test. So now we are going to the other test. So the rest of the next topic we're going to discuss is we have another type of test. So we have talked about integral test. There will be another two more tests, the comparison test and the ratio test that we are going to discuss today, and also alternating series and absolute conditions. I think this will be different topics or different methods that would that you can use to check the convergence of other forms of sequences. The sequence could be very complicated. So far, the integral test is applied to sequence which is decreasing and is all positive. So the next test we are going to learn, the comparison test, is also limited in the sense that it only applies to series where the terms are positive, right? So if the terms are, that contain negative terms, so you have a sequence that has positive, negative, positive, negative, 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 positive, negative, then the integral test that we just learned would not be useful. Then so is the comparison test and the ratio test that we're going to talk about now is only applying to series that has only positive tests. So there are two tests in the comparison test. So first is what we call the comparison test. The second is the limit comparison test. There are actually two tests here, and the ratio test, there's only one test. There's actually one more test or two more tests, which is called the root test, power root test, or something like that. I have omit that because we have too many tests to talk. So I've omitted a few tests. However, these tests will be sufficient for you to check whether a series is convergent or not. Now you need to master this test because this has the test 11.6, 11.5, 11.4 will be used. You have to use this test to apply to power series and also Taylor series. So if you do not know how to use the test, then you will have problem to understand power series and Taylor series. Because when you form the Taylor series or power series, you have to prove that you have a series that converges to some function. And in order to prove that the series converges to some function, you need to prove that indeed the series converges.